My name's Boban, and I'm a fourth year actuarial finance student. That's over in the CBE. I've done a lot of statistics during my degree, like a mind-boggling amount of unnecessary statistics. And there's a lot of boring stuff, there's a lot of interesting stuff, and I've tried to distill some of the more plainly accessible, interesting stuff into this nice presentation, which I've very originally called Lies, Damn Lies, and Statistics, Data in the Modern World, and How People Will Lie to You. Yep. Okay, so why statistics matter? So I start with the quote by Benjamin Disraeli. So there are three kinds of lies: lies, damned lies, and statistics. And so, on the face of it, you know, statistics is this kind of inaccessible thing that people use to lie to you. And that's what I'm going to argue, but it's really pretty necessary as well, especially because we live in a world with just a mind-boggling amount of data. And I think probably the computer scientists or something can tell me, but there's some stat about, like, you know, in the past 2 years, the internet's generated as much information as, you know, the previous 4 bajillion years. Probably not as much useful information, but still, information nonetheless. And given that we're also specialised and also different, we need some kind of quick way to share information and to encode information. And that's where statistics comes in. So statistics is just another form of communicating. So we need to understand things, so we need statistics if we want to understand big, complicated things that we're not particularly specialised in, or we can't grasp in their entirety. Yep. So what I'm going to talk about is going to split up into about 3 different areas. So the first topic is how surveys are conducted. Second is how information is interpreted. And the third, my personal favourite, how the information is displayed, where I'll get to show you nice little pictures and tell you which pictures are good, which pictures are not good, objectively. Yes, what?
Do you mention the ABC News?
No, although I could have done an hour on Alan Kohler's terrible, terrible abuse of financial data. I decided not to, because I don't really get off on a tangent, and that wouldn't be fun for anybody. Incidentally, if you guys want to say something during the speech, literally just yell out at me, and if it becomes annoying, I'll just yell at you. The system will kind of self-regulate that way. Yeah. So we've all seen surveys that we know are just terrible. Like, you know, in every Colgate ad, you have, you know, 9 out of 10 dentists recommend Colgate, and it's truly terrible because you know that there are many things wrong with that, and I'll get to that. But to start off with, I might just, you know, go back to basics. So what's the point of a survey? So I might draw this on. Am I good to go over here?
Yeah, you're not.
When we do statistics, we have 2 things. We have a sample and a population. So the population is the thing they actually want to study. So Ukrainian hairdressers, you know, 3-armed drummers, you know, whatever you want. And we call that kind of like a big universe. That's our population, right? That's everyone who could possibly fit into any category, right? And what we do, so every few years we have a census in Australia, obviously, to do a head count, to do income data and stuff like that. That's really, really expensive and really, really time consuming, especially for big groups. So what we do instead is we do surveys. And so we'll just take, you know, a random sliver of the data here. What we do is we figure out what these guys are all about and what kind of characterizes them. And then what we do, in an act of logical amazingness, is we extrapolate to everyone else what we do about that. And really that's the only cost-effective way to do anything, the only time-effective way to do anything, which is why surveys make sense. So then the question is, how do you even do a survey, right? So if I want to say something about this whole group here, about the rectangle, you know, A&U students, right? And I survey 50 of them, I need to make sure we have what's called a representative sample. And that's really important. So if you actually want to say something about this whole group of people, then you need a bunch of people here, you need to survey a bunch of people who actually represent the whole people. And that's usually where the survey data tends to fall apart. And so whenever you're looking at survey data, you know, you need to ask the person a few things, you know, right? Who did you choose? Because the way people are chosen is really important, right? whether they're self-reported, right? So if you've ever seen data that's self-reported, say about when people leave a university, and say the ANU wants to make itself look fantastic about how much their graduates earn after uni. A lot of that data is self-reported, right? So what you have, let's say you have the moneyed people over here and the not so moneyed people over here, right? And you're doing a survey of how much they're earning, right? Who's going to report and who's not going to report? If you're earning a little bit of money, you're probably feeling a little bit bad that the ANU sent you a questionnaire reminding you of how little money you earn. So you're probably not going to report terribly much. Whereas if you earn a ton of money, you'd be really happy to say, yeah, I earn like $100 million a year. So you'd be happy to report to the survey, right? I mean, what's the loss to you? You just get to reaffirm your self-worth. And so you always got to be very careful about who is picked in these survey groups. And that's where a lot of things fall down. Another example is bad election polls in the US. So election polls are really quite notoriously bad in some places by a lot of very distinguished polling companies. So for example, there was a particular, I forget actually which one, I think it was Rasmussen, decided they would only call landlines, right? Which is a really terrible idea, because it oversamples the old and apparently the conservative. So in states where there was maybe 2 points of difference between the Democrats and the Republicans, oversampling on landlines is 4 points of error, which completely wipes out any kind of meaning that you could have. Also, people who do surveys are just crazy. Someone walks up to you in the street and asks you, "Hi, I'm someone you don't know. Can I ask you a question?" Who answers those people? They could be easy. They could be anyone to take your data. Or they have an agenda. So say you're reporting your own income at a company online. So there are lots of websites where you can report what level of income you are on at a company. And the only two people that really go for those is the really, really discontented people that got fired by the company, and the really, really contented people who will be hiring you. So what you tend to get, whereas in actual fact, the salary bands from here to here, you tend to get a salary band from here to here, and that's not good for anyone. Yep. Also, people just lie. Even if you give them the survey, even if you give them a representative sample, if the question is embarrassing enough, they'll just lie to you. So, for example, I guess doing a survey of STD distribution in a monastery, that would be that would be a very embarrassing question. And so you actually go to quite extreme lengths even to get rid of that embarrassing question, because even people who who do won't do it, even under strict assurances of privacy. And so you actually get kinds of scenarios where what will happen is, so if you flip a coin, right? And if it lands heads, then you answer yes to the STD question no matter what. And if it lands tails, then you answer the truth, right? So that way you have at least half the sample answering yes to the questions, which will make them feel better, because if someone dredges it up, they're going to say, "Oh, I flipped a coin." But that actually, under the right circumstances, actually gives you better data. Just because of how embarrassing the questions are. You can kind of like take the coin toss out of the process. And in income, the reason that the census uses income bands as opposed to exact income, other than it being difficult and people take a lot of time, is that people just over-report on it just to make them feel better, make themselves feel better. So instead of writing like $71,000, if you give them the band 70 to 75, they'll just be like, "Oh yeah, I can write that down because I'd like to feel that I have $75,000 of income." People, I mean, my psychologist friend knows it better than I do, but people are really weird. Then finally, even if you get all that right, there's the matter of the truth, the whole truth, and stuff like leading questions and how you phrase things. And Zach, I'd like you to flick to the first video if you can.
To say something new and radical in the broadcast.
What, that silly grand design? Bernard, that was precisely what you had to avoid. How did this come about? I shall need a very good explanation.
Well, he's very keen on it.
What's that got to do with it? Things don't happen just because prime ministers are very keen on them. Neville Chamberlain was very keen on peace.
He thinks it's a vote winner.
That's more serious to know. What makes him think that?
Well, the party who had an opinion poll done, it seems all the voters are in favour of bringing back national service.
We'll have another opinion poll done showing the voters are against bringing back national service.
We can't be for it and
Oh, of course they
against.
can, Bernard. Have you ever been surveyed?
Yes, well, not me, actually, my house. Oh, I see what you mean.
Bernard, you know what happens. A nice young lady comes up to you. Obviously, you want to create a good impression. You don't want to look a fool, do you?
No.
No, so she starts asking you some questions. Mr. Woolley, are you worried about the number of young people without jobs?
Yes.
Are you worried about the rise in crime among teenagers?
Yes.
Do you think there's a lack of discipline in our comprehensive schools?
Yes.
Do you think young people welcome some authority and leadership in their lives?
Yes.
Do you think they respond to a challenge?
Yes.
Would you be in favor of reintroducing national service?
Well, I suppose I might.
Yes or no?
Yes.
Of course you would, Bernard. After all you've told you can't say no to that. So, they don't mention the first 5 questions, they publish the last one.
Is that really what they do?
Well, not the reputable ones, no, but there aren't many of those. Alternatively, the young lady can get the opposite result.
How?
Mr. Woolley, are you worried about the danger of war?
Yes.
Are you worried about the growth of armaments?
Yes.
Do you think there's a danger in giving young people guns and teaching them how to kill?
Yes.
Do you think it's wrong to force people to take up arms against their will?
Yes.
Would you oppose the reintroduction of national service?
Yes.
There you are, you see, Bernard. The perfect balanced sample. So, we just commissioned our own survey for the Ministry of Defence. See to it, Bernard.
I won't say any more of that topic because I think that covers it like just perfectly. Yeah. And then you get so the thing is, depending on which one of these groups you pick, you get a different outcome, right? So say you're looking at average income, right? And you pick this group, and say you get an income of 50,000 here. That's kind of like an artifact in the way that you just chose the group, right? So what you can do instead is you can pick this group and say, you know, this is $70,000. So even in well-conducted studies where people don't lie, and the truth, the whole truth, and nothing but the truth, you can still have different average incomes depending on, you know, how you do the salary survey. And it's similar in medical trials, right? So you can have a lot of surveys or trials where, you know, the drug looks effective, others where the drug looks ineffective. And what you have to do is then you have to take all of them together in what's called a meta-analysis. Look at all of them and then bunch them together and see what happens there. So you group them all together and see what's up. But sometimes the surveys just don't turn up. So here we have what's called a funnel plot, right? And this is a little bit complicated, so I'll talk through it. Here is the standard error. This is essentially a measure of how big things are. So here things are quite small. And here the surveys are quite big. That's essentially what it is. So what you expect to happen is in the really small ones, you get a lot of variation, right? Because if I just took Zach's height, and then I say, you know, that's a survey sample of 1, right? And I took any one of yours, the variation there is going to be quite high. However, if I average this half the room, that half the room, it's going to be much, much closer together. And so what that means is as I go up, okay, this is essentially how effective it is. So this line here means completely ineffective. This means effective, this means ineffective. So what happens is, as the surveys get bigger, they converge to the same result, like this. But if they're small, it's a lot of big results. And if they're big, there's a lot of results that are clumped together. Now, over here is an example of a survey where this half just kind of doesn't exist, right? So clearly, these samples have been taken out to make this effect look bigger. And now to really mess with you guys, this is an example of publication bias. That's what publication bias. And this is analysis of publication bias. of publication bias, which means all of these have been taken out. There is a problem there. I'll field questions if you guys want to question me on that one.
Just
Next.
a comment on your medical thing.
Yeah.
The other thing that's amazing is how many drugs are that are not for young men are tested on men from 18 to 25. Because if you want to see no side effects, you give it to men who are 18 to 25.
It's exactly about choosing the representative sample, right? And if you're testing a drug on, for heart disease, you should test it on 65-year-old men generally. Probably a few women as well, but they tend to, it's terrible the way they do some of these things. Next. So now we get to the interpretation of data, and I'm going to cover the most dangerous word in statistics. That's average. That is probably the most dangerous. Firstly, of what? Secondly, of which average? Then I'm going to cover a few other things that we'll get to, I guess. So next one, averages. Now this one I could fade in, fade out side effects, so I've learned them in year 5. Yep, keep going, just keep clear. So here we have, so I'm going to construct a hypothetical department. And at the head of my department is the mustachioed Adonis that we have the pleasure to call our Vice Chancellor, Mr. Ian Young. And he actually, based on some data I got from the Australian, earns about $800,000 a year, which is pretty good. Ian Young, the sartorially splendid Terry O'Neill, who's the head of the school that I'm in, he's the head of the CBE. He earns about $200,000. In my hypothetical department, I will have 2 Terry O'Neills. Preferably clones of one another. That makes more sense. Yep. Then I will have 3 C-level academics, which by the ANU pay scale puts them at about $100,000 of remuneration. And I'll also have 5 A-level academics. These are like your postdocs, your tutors. They earn about $50,000 a year. So, what is the average? It depends. So, first average, the arithmetic mean. Okay, so this will be a bit of a throwback to all of you guys who haven't done maths in a while. Just out of curiosity, what's the maths level of this room? Who is doing what they would call a quantitative degree? Keep your hands up. Who's doing it what they call a technical degree? Okay, who here did maths in year 12? Okay.
Does general count as maths?
That's enough. So the mean, what you do is you literally add up all the incomes. So that's 800,000 plus 2 lots of 200,000 plus 3 lots of 100,000 plus 5 lots of 50,000, and you divide it by the number of people in the sample. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You do that, and that's approximately equal to $159,000. Now, just think about what's average supposed to mean? When you hear average, you think in the abstract. What information do I want to get across to you if I tell you the average? I want to tell you what's statisticians call the central tendency. The tendency of where's the middle? Where do things bunch up? Where do things tend towards some kind of center? And 159,000 actually does a really terrible job of it, because that's the line between my 2 Terrys and my 3 Cs. So as you can tell, only 3 people earn above $159,000, and 8 people earn below that. So it's a pretty crummy kind of measure of if you want, a kind of typical group of ANU academics. But of course, the ANU will report that the average academic earns $159,000 a year in this circumstance. Something that's pretty sensible is something called the median, and that's the middle score. And the way you do that is you literally, so I had 11 people in the sample. So I picked this guy, this first C here, because he has 5 people above him and 5 people below him. So he's in the very middle, and that's a much more indicative kind of number if you want to know what's kind of a fair, like a reasonable, typical kind of salary in this department. Because you literally have 5 either to the left or to the right of you, more or less than you. And it's not kind of skewed or made really, really big by, the moustache guy. Or, another way you could go is you could go for the mode, which is the most frequently occurring score. One more. And so, this is the one that the union would use in negotiation. So they would say, oh yes, well you have Ian Young here at the top earning unseemly amounts of money, our typical ANU academic has to go on near $50,000 a year. And that's probably not fair, right? Because while there are 5 people on $150,000 a year, you know, there's probably some career advancement there. I don't think that's really representative of the entire sample. And I could have put these 5 people whichever group I wanted, right? So it doesn't really matter. So that's not really a good sign. But these will be used. And they're used everywhere. And they're used everywhere people are trying to lie to you. And there are 2 other kinds of mean that I'll do question and answer if you guys want. There's so many different kinds of averages. Average is the most dangerous word. Whenever anybody says average to you, they're probably trying to take money from you. Just watch out, watch out. Simpson paradox. This is one of my faves. This is a subset of what statisticians call the ecological fallacy. And I could do it theoretically, but it's much better with an example. This is from an actual survey, which I failed to reference. Here we have, I believe this is Florida's death penalty cases in 2002. Here we see Caucasians, were someone of Caucasian descent, was the defendant in 430 of those cases. And they were convicted in 53 of those cases, leading to 11% application of the death penalty. Likewise, 176 African Americans. Oh, sorry, that's wrong. What I meant to say was 430 plus 53, the total number of people. And this is the percentage of that got the death penalty applied to them. So 176 had no death penalty, 15% had death penalty, so the percentage of the death penalty was 7.9. Trust me on these numbers. But if you've ever looked at the US justice system, you know that African Americans are not consistently renowned for being, having the justice system be nice to them. And that's what we actually find when we look a little bit deeper into the data. What we find is that this is far too high level an analysis. So then what we do is we break it up. So we say, okay, we have the defendant's race here, but what if we put in the victim's race as well? Okay.
Press the button.
So we'll see what happens there. So now this tells a very, very different picture. So now let's focus where the victim is Caucasian. Here. Right? When a Caucasian is convicted, so when a Caucasian is tried, the percentage that have the death penalty applied to them is 11.3%. Whereas the victim is still Caucasian, the defendant is African American. The percentage of the time the death penalty applied is 22.9%. Alright? Okay. Let's keep going. So when the victim is African American and the defendant is Caucasian, essentially they never get executed. Whereas when it's African American and African American murder, the African American defendant gets executed 2.8% of the time. So as you can see, regardless of whether it's Caucasian, the defendant is Caucasian or African American, when the victim is Caucasian or African American, if the defendant is African American, then this number is higher than this number, and this number is higher than this number. So there's Simpson's paradox. If you break it up, you have a higher death rate if you break it up by the victim. But if you look at the total thing, it looks like a lower death rate. And the reason for that is African Americans kill African Americans way more than they do Caucasians. So what happens is that this kind of drags the rate down, leaving you a false impression of what the data says about Caucasian versus African American death penalty sentences. And this turns up everywhere, especially university admissions data. Stanford had a very famous case about that, and I can talk about that in Q&A if you'd like. So always be careful. It's called the ecological fallacy because this is like birds and butterflies and bees. Like this is the whole kind of ecosystem here. But when you look at constituent parts, it's a lot different, and a lot of people make a lot of mistakes by messing this up. Now, SIDS. I don't mean like sudden infant death syndrome. So, I'm going to start off by talking about 2 games. The first game is going to be 2 independent die rolls, right? So you roll your first die here, and then you roll your second die. And you can get 36 different possibilities. That's 6 times 6 different possibilities. You can get 1, 1, 1, 2, 1, 3, blah, blah. All of you played Monopoly. So the probability of double ones is 1 in 36, right? And another way you can get that is, so by that what I mean is there are 36 outcomes and only one of them is a double one, right? And these are all equally likely. So I have a 1 in 36 shot of getting a double one, right? Another way to calculate that, and try to get a better pen. Is that to say, green, as 1 in 6, it's probability of getting 1, 1, and times 1 in 6 again for getting another one. And that's because, we can do that because these are independent, right? What you roll on this die doesn't really affect what you roll on this die, right? They're kind of two different die rolls. So let's have a look at game 2. Die roll followed by repetition. So what I do is I roll a dice, just one. 1, 2, 3, 4, 5, 6. And say I get a 1. Then I write down a 1, and then I just write down another 1. Right? So all I get is doubles. So if I get a 2, I write down another 2, and I get 2, 2. If I get 3, I write down another 3, and I get 3, 3. Right? So my possibilities are just all these things here along the diagonal. Right? And in that case, the probability of a double 1 is just 1 in 6, because all I have to do is roll a 1 once, and then I can just write another 1 after it. So this is an example where they're not independent, right? Where your second number is very, very heavily affected by your first number. And how this links to SIDS is on the next slide. So this is a bit of a PowerPoint hell here, but it's pretty important. So at the trial in 1999, solicitor Sally Clark, so she's the defendant, accused of murdering her 2 sons, Meadow, who is a medical doctor, testified that the odds against two such deaths happening were 73 million to 1 shot. A figure which he obtained by squaring the observed ratio of births to cot deaths in affluent non-smoking families. Okay, I'll try and break that down to you. And that was approximately 8,500 to 1. What game is that like? So essentially what he did was 1 in 8,500 times 1 in 8,500. That, if you remember, can we flip back to the last one? That was like game 1 here. This is where your first die roll is not affected by your second die roll. So what the expert witness has just done is he's assumed that the second SIDS death is in no way related to the first SIDS death. Now anyone who's done any kind of survey or medical training or any kind of, SIDS is a very, very poorly known condition. It's very rare. And you lose a lot by assuming that your second one is in no way related to your first one. And what that does is it drives up this figure like really, really dramatically. And she did end up getting convicted, and on appeal it was squashed for other reasons, for legal reasons. But it was a very public trial, and it showed a very, very kind of startling defect in expert witness, who was supposed to be quite good at this. And this was a very, very big deal for a while. So statistics has consequences, guys. You've got to be really careful. Yeah. So, and this is just, I love XSAC5001, so this is a good one. Oh, wait, actually, next one. Okay, let's watch this one. So, polio and ice cream. So, I'll yield to the Freakonomics guys for this one. Who was over this?
Well, hi there, boys and girls. This is Captain Kangaroo. Say, I'd like you to meet a friend of mine. So, it's lots and lots of fun to have a pet you can run and play and jump with, isn't it? But did you know that there are some boys and girls who can't run and jump and play? It's all because of a thing called polio.
When I
think of bad historical assumptions about correlation and causality, I think of polio 100 years ago, when it was this horrible mystery that it was, claiming a lot of lives, and it was really scary because it mostly struck children. And there was a strong line of research that suggested that ice cream caused polio, that ice cream consumption caused polio.
Here comes Mr. Softy, the soft ice cream man. The creamiest soft ice cream you get from Mr. Softy.
The reason that correlation was thought to be causal was that polio spiked in the summertime for reasons that really weren't very well understood, but it did. And ice cream sales spiked during the summertime. So these researchers had seen that whenever there was a lot of ice cream being sold and consumed, there was a lot more polio. And so there was really literally the beginnings of this kind of ice cream persecution to try to stomp out polio. And it sounds ridiculous, but you see it all the time now, people trying to fight against or build up something that they're sure is connected to something else, which it turns out just isn't.
I think that pretty adequately described. So just because two things move together, guys, it doesn't mean that they get caused by one another. And this is a problem that's very, very kind of widely distributed. So essentially what you had is you had polio, you had ice cream consumption moving, and you had polio moving at the same time and in the same direction. And so so what they kind of poorly concluded was that they had ice cream causes polio, whereas they had a third variable, that is the summertime, that caused both ice cream and polio, or caused polio cases to shoot up and caused ice cream consumption to shoot up. We'll skip the audience involvement bit because I'm going a bit over time. So correlation versus causation. Just because they move together, it does not mean that one thing caused the other. And that's a mistake that a lot of people make, a lot of smart people, otherwise smart people. Differences that don't matter. This one's fun. So essentially the kind of idea behind probability statistics, you kind of try and quantify uncertainty, right? And what's really uncertain kind of every month is that economists fret about the unemployment number. So I just looked at the last survey, and they had that there were 47. Oh, so that's very poorly done sentence. That 47,000 jobs were created in the last month, right? But they do that through surveys, right? So they're not entirely sure how many jobs are created. So this month the number was 47,000. So what they do to help you out, to show you how uncertain they are, is they constructed what's called a confidence interval, right? Where essentially they say 47,000 jobs is our best bet. But what we're going to do is we're going to give you a band, say 40 to 60 or 30 to 70, where we're 95% sure that the number of jobs is between that lower bound and that upper bound. So so you could have that between 30,000 and 50,000, 60,000, right? So that's what's called the confidence interval. So we're 95% sure that the actual number, so 47,000 is not the actual number, it's some number that we can't get, is between 30 and 60,000. So that's just one that I made up on the spot. Guess, does anybody know what the actual size of the confidence interval is? Does anyone know how uncertain the Bureau of Statistics is about the employment data? Anyone?
Like 10 to 100,000, or?
So 10 to 100,000, that's one guess?
Like 10,000 to 100,000 or 10 to
10,000.
10,000 to 100,000.
Okay, right.
That's one. Any other guesses? Come on.
Between 0 and some.
0 and some. That's another guess. Anyone else? Come on, guys. Don't be shy.
Minus 100,000 to plus 100,000.
That's pretty good. The actual number is minus 10,000 to plus 110,000.
Oh, jeez.
Oh, God.
So every month they report 47,000 jobs. If someone says 48, they get corrected, so they say 47 instead. And you've got 50,000 either way. Well, it's really funny. So the unemployment rate, I believe, went up by 0.2%. No, 0.1. I think 0.1% recently. Guess what the confidence interval was of that? Anyone?
Probably about 2%.
Well, close. So it was between minus 0.3%, which would have actually been the worst employment month in a decade, to 0.5%, which would have been the best employment month in a decade. So the Bureau of Statistics tells you it's 95% sure that this month was between the worst month and the best month of the past decade. Which is really troubling when you think about it.
No, what's troubling is the series they won't even run anymore because the data is so dodgy.
I mean, it's actually all there, but nobody bothers to read that stuff. That's statistics, right? Election polling is even worse. So what you'll have is you'll have, so you'll have a swing state. One candidate's polling at 51, and the other's polling at 49. Well, they neglect, and then the next week, it's switched around. Candidate A is polling at 51 instead of candidate B, and candidate B is polling at 49 instead of candidate A. Well, they neglect to tell you that even the biggest ones, like the New York Times one, has a plus-minus of 3, right? So nothing has actually changed there, probably. But yet, it creates jobs for pundits on talk shows, like talking about, this time, Obama's getting up to this state, thanks to this new poll that really doesn't mean anything, or Romney's getting up in this state. And historically, the Treasury has been quite bad about this, but I'm quite happy because they put in confidence intervals for the first time in the mid-year economic forecast in December. So, next page. So, they're giving you a 90% confidence interval. So, sure, 1 in 10%, 9 out of 10 times it will fall between this band and this band. So, 9 out of 10 times, it will be either the worst or the best growth that we've had in the past decade. And the past decade has been a really, really turbulent one. And imagine the 95% confidence interval. If you want to be sure, 19 out of 20 times, you have to make it even bigger. Which is, so every time they fret about these numbers, don't live your life month to month. You gotta look at the long-term view of these things.
How do you ever watch election coverage?
Oh, it's kind of fun.
It's funny.
It's kind of like how you so if there's any science students who watch like Star Trek or something, and they're like, oh yeah, the tractor beam totally works like that. I think it's much the same thing. I feel it is. So yep. So my favorite bit of the talk are the graphs, the do's and don'ts. And we'll go through graphs, the charts, whatever you want to call them, statistical displays. So the whole, so we'll go through. I'll introduce you to Mr. Edward Tufte, who is the kind of the cross between Buddha and Jesus of the statistical graphics world. He's kind of like he's the be-all and end-all of statistical graphics. I'll introduce you to good graphs and what they look like. I'll introduce you to, this is my favorite part, really, really terrible graphs. Some very close to, some very close to home.
No ABC graphs, really?
Sorry?
No, none of the ABC's pie charts?
No, I didn't want to go on a rant. Not much of one anyway.
That's what the question section is for.
That's what the question section is for.
And it's all on camera.
And so then I'll show you, then I'll summarize the general characteristics of good graphs and bad graphs. So this is one of my favorite quotes in all statistics. So this is by Edward Tufte. Visually attractive graphics also gather their power from content and interpretation beyond the immediate display of some useful numbers. The best graphics are about you useful and important, about life and death, about the universe. And this is my favorite line. Beautiful displays do not traffic in the trivial, right? And that's tough. It's tough to make a display that doesn't traffic in the trivial, if you're on a limited time frame or a limited budget. But that's why you get a lot of crappy graphics. But to start off with, we'll look at some of the good graphs. So, oh, that's not supposed to be there. Keep going, just click through. That's a bad graph, that shouldn't be there. Oh yeah, this part's fun. This is a demonstration. So, get out of this. Okay, this is some data that I've generated. And, sorry, let me preface it with something else. So the whole point of statistical graphics is that you can see a table of numbers, and that's fine, that's technically correct. The whole point is we're good at visually perceiving things. I'm happy my psychologist friend left, because she could have said some things maybe. But you can visually see a ton of information that would be really hard to display in a table, really hard to interpret in a table. But you have to do it properly, and this is to do with the doing it properly bit. So I claim here that there is a pattern. Can anybody see the pattern?
I saw it in my stats class, I would say.
Ah, yes, you. So this is stolen almost wholesale from a guy called Michael Martin, as is a lot of my talk, actually. So he's fantastic. If you ever have a chance to do a course with him, do it. Yes.
Is there, I can sort of see two potential ones.
Mm-hmm.
Either a pattern of extremes with ones at really low numbers and really high numbers, or two, what's the word, straight lines running diagonally?
That is technically correct, but not enough to get full marks. Okay.
They're kind of clustered a little bit closer together towards the bottom
That's true.
corner of the graph.
So that's what marks it. That's correct, but that's not the pattern.
Is this a graph of almost total insignificance, given that the bottom scale is 10 and the top scale is 1?
No, there is some significance to the graph, and there is a pattern here. I've never seen anyone pick it though.
Well,
and
stop asking us.
Kate's laughing because she knows it's happening.
I've seen it too.
Yeah, no, I've seen it as well.
Okay, fantastic. So, let me show you guys.
Maybe like a train or something.
Can you start see the pattern yet? Anyone? No, not yet. Not yet. No, not yet. Not yet. There we go. And that just makes you feel so stupid. And you're right, because of the way I've done the graph, so it's a sine, it's to the mathematically inclined, it's a sine curve, and I've added 1, so you don't figure it out, it's a sine curve. And it does tend to, the way the function, the way the mathematics does it is so that it does tend to cluster around the bottom and the top.
Can you just zoom it out a bit again so we can that stupid?
Oh, you won't be able to. So actually, that's a very good point. So I'll show you what most of you probably did, and what you shouldn't have done. So a lot of the way I had my stats lecturer explain it to me is that what most people do when they look at patterns is they do nearest neighbor matching. So you go, okay, this is the start, so I'll start here, and then I'll move to the closest one, and then I'll move to the closest one, and then I'll move to the closest one, and the closest one, and I can't see a pattern anymore. And that's okay. You're not supposed to do it. I mean, the pattern is like that. But it's very difficult to say. I haven't seen anyone who's managed to pull it off yet. I don't think that human brains work that way. So that's just a really quick introduction of why graphs have to be right. So I just changed the scale, and that's really bad. It depends on what you're doing, but it could be really bad. And here's another example. So this is a chart that I stole from a book called How to Lie with Statistics, which is a really, really great book. I recommend it. And it shows, I believe, national income in some year in the early 1950s. And it's kind of cut off. It's like got January, February, March, April, May along here. Doesn't matter. So you see kind of, this graph shows kind of gentle ascent from 20 to 22 billion dollars. Right, with a nice little contented guy in the background who doesn't really do anything. So that's kind of a fair graph. I mean, it's kind of bad because you've got a guy in the background, but that's okay. But what if we want, that's kind of like gentle. The slope is kind of too shallow here. So what if we want to tell a different story? Next. So what if we just cut out the bottom bit? What we see now is it's still the same slope, but now it goes from like a third of the way up a graph to like 2/3 of the way up a graph. And if you're just flicking through this, you're like, wow, that's a little bit more impressive. But why stop there? You know, we can have more fun than that. So now we just stretch it out. And now the gentle 10% increase is a shocking 10% increase. It goes from the bottom of the graph to the top of the graph. And this guy is equally confused as you are. So it's amazing how our perceptions can change just with the change of scale. This is something that it's still technically right, but those two, the difference between the graph I just showed you and the graph I showed you at the beginning is night and day. So pattern, sorry, on that bit. This is an example of a fantastic graph. So it's a bit hard to see because there's a lot on it, and it's kind of poor resolution. But this is Napoleon's campaign in Russia. I believe this is about the Polish border here, or what? I don't know if Poland was a thing there. And so his army starts here. So this is his army going in, and this is actually superimposed on a map. So from Poland to Moscow. And here his army size is this, and actually has the numbers here, but you can't see it because it's quite low resolution. And then it shows, bits splintering off, bits coming off. So, and then it shows his army kind of shrinking quite dramatically. Shrinking and shrinking and shrinking. until he goes and he reaches Moscow here. So you've got two sets of data. You have geographical data, you've got army size, actually three. Geographical, army size, and army split, where his army splits off and how much it can split off. And then you see, in a different colour for convenience, the retreat. And this is quite bad, because as he retreats, his already kind of depleted army gets smaller and smaller and smaller and smaller and smaller, joined by a few of these guys, it gets smaller and smaller. And overlaid on top of that is, so on the retreat, it gives you the temperature scale. And I believe this is 0 here, and this is minus 30 degrees. In time measured was usually in the early morning. It's probably the coldest. And that's why a lot of them die. So this is an example of a fantastic graphic. This is Tufty's favorite graphic. And it's because it's not trivial. Like, this is really important stuff. This is life and death stuff. And it shows like 5 different sets of data on one kind of pretty straightforward to read chart. I mean, everyone kind of gets army goes that way, numbers, geography, cold. So that's good. That's really good. That's a really effective chart. Next one. This one is, I should have cropped it probably. This one, although it doesn't look on its face to be particularly effective, is probably one of the most effective charts. So you've seen this one before?
I do biology.
You do biology? So who's this chart by?
Jon Snow.
Jon Snow. What did Jon Snow do?
Nothing.
He knew nothing.
He figured out the location of the water pump that was causing cholera in Broad Street.
By tracking the number of deaths.
By tracking the number of deaths. And this is fantastic. So, for convenience, I've circled the pumps here in red. You kind of see whenever it gets kind of close to a pump, you know, kind of the deaths stop. And here you have circled the offending pump. So whereas this isn't actually enough information to kind of say, oh, this is the pump, because say it could be something on this street corner and that street corner or something like that. It actually led to some really important outcomes. He eventually found out that it was, I think he moved the pump handle, and then he like got all the water out and found out it was like baby feces or something.
Dead eel.
Dead eel. And so you notice you know, in a way that simple death data couldn't have shown you, you see the huge clustering just around here. You know, you see in the middle of that cluster a pump. And so that's really good life and death stuff, fantastic graphing. Now we move from the truly sublime to the truly terrible. This is probably one of the worst graphics ever. So let me explain this, because again the graphs turned out kind of low resolution. So this is the graph, and this is one that I've done. This is the kind of crap that turns up in some magazines. So this is age structure of student population, right? And so this is 66 here. This is 67 here. This is 68. And it jumps from 67 to 34, 33. They were nice enough to put a little break there. That's quite nice of them. And what it says is the percentage of students who are under 25 is this point, this point, this point, this point, and this point across a few years, 1972, 1973, 1974, 5 and 6. And then the percentage 25 and over, which is just 1 minus that percentage, just flipped here, kind of for funsies. What's also done is they've introduced a third dimension, which is terrible because this actually adds nothing. So this whole bottom adds nothing. This dimension adds nothing. He can't draw these lines because he has no idea what it looks like in between there. And this chart shows 5 numbers. This is 5 numbers. Go back to the one before. This is like 500 numbers. You know, this is 5 numbers, and this is bad. I did it like this. Like that's all it is, guys. And this is really bad. This is just snow. So you've just wasted so much ink there. The eye doesn't know what to do. It doesn't know what it's doing. It's so confusing.
We need another set of rules on that picture channel.
Third dimension, meant to even work with that.
It doesn't represent anything. It just doesn't look funky.
It's meant to look pretty.
It's meant to look pretty, which is terrible.
I presume that it just plateaus for a bit between 74 and 75.
Nobody knows. You can't tell. So that's a much more sensible graph that I've done instead. Okay, next. Okay, pie charts. Now, a lot's been said about pie charts, and there's a lot of misinformation about pie charts. And I just pulled a random one from the internet, and this is what normal people see when they see a pie chart. And so it's just a regular pie chart, you know, browser use, blah blah blah. And the next slide is what statisticians see when they see a pie chart. The point here, is anyone nerdy enough to know who that is? Not you, not you.
That's a Thor.
No, that is Elvis Prince of Undeath, but much the same effect. I despise, and most statisticians despise pie charts. And I'll show you.
Paul has started including them for the first time in years. He now includes pie charts.
Who?
ABC guy.
Hey, Alan Kohler.
Yeah.
Don't get me started.
he now includes pie charts as well.
You know.
Does he know you're planning on murdering him?
No, but he's definitely swift.
He does, however, know that the sample size of statisticians who are planning on murdering him.
I'm going to go through pie charts and tell you exactly why they're bad very soon. But let me tell you, kind of in a feelings way for me, how bad pie charts are. Let me tell you how bad a dream I had about pie charts.
Single lady.
To the right. And this happens not very often, but somewhat often. And so I had this dream. So I'm going to be an actuary, and I'm going to Sydney next year to do some actuary stuff. And so I had a dream, you know, a professional dream where I was a manager at an actuarial firm, which is very nice, very good. That's not the punchline. I had an employee come in, and he showed me this report. I loved the report until I got to the very last page, and I found a pie chart in my dream. So I fired him. The really weird bit is, you know how you kind of wake up and you're like, you know, you shudder if it was a bad dream? I kind of went, that was a happy dream. That was a happy dream, guys. So, please, no pie charts. Now we'll start going through. So, just a sec. So, pie charts are a really bad way of displaying data, and only the truly kind of statistically inept or actually malicious. They can either be ignorant or malicious. And truly the ignorant or malicious, only the ignorant and malicious use pie charts. So next slide. This is the ANU income statement from 2013.
Oh my god.
Now, let me go through to the point why this is this is just terrible, right? So, the point of this is presumably to compare all the different segments to each other, so that you know that National Institute's funding is, say, bigger than scholarships, say. And it kind of does that to a mild extent. But, first of all, unsorted. It doesn't go smallest to largest, no particular order, not even alphabetical.
There are two separate things labelled 1%. One of them is twice as large as the other.
Next thing, there are two separate things labelled.
Zero actually shows up.
Yeah, 0 is here. There's no pi here.
But there's another 0 that has pi.
Rounding error.
Yeah, so your rounding error is A. Secondly, so 0% is different from 0 and maybe kinda 0, and 1 and maybe kinda 1. So first of all, so there's no way to compare them. And even when you try to compare them, the human mind is terrible at comparing areas and angles and stuff. That's why protractors are so much more kind of, they kind of be more useful than rulers. Like, you kind of know what 30 centimeters is, but it's really kind of hard to know what 30 degrees looks like, you know, with relative size. So this says very, very little. They helpfully provide all the percentages here, but I don't really get anything from the chart. Something better would have been to just put this in a table and order it largest to smallest. That way you would be able to find out exactly what you wanted to know, and you wouldn't have to have used all this space, essentially just to confuse people. Or alternately, so I've redone this chart like this, and I've removed some of the zeros because they don't exist.
They don't exist, but they're just so small that they get rounded off.
Yeah, so I've removed a few, rounded off, and this is just a little bit better, right? This way, you can kind of tell that, you know, investment revenue is 4 times smaller than, you know, than your National Institute's funding, and that's just much, much more palatable. And I don't claim this is the best chart, but this is, you know, so much better than the one before it. Now, there's pie charts. That was an exploding pie chart, and while I appreciate the sentiment of an exploding pie chart, this hasn't in practice. The other great evil of pie charts is the next slide. 3D. And this is from our own treasury, guys. Our own treasury. So the reason.
Hang on, is this the budget?
This is the budget of our country.
I have seen the enemy.
Luckily,
That's the 2010 Intergenerational Report, isn't it?
That is from, no, I believe that's from the 2012 budget, but don't quote me on that. It's one of the more recent budgets. The Intergenerational Report, however, does have pie charts as well.
I didn't remember that broke us.
So, the problem with this one, apart from it being a pie chart, is that it's a very malicious kind of pie chart. Because while regular pie charts, you can't compare area, but you try, here you're comparing volume on an angle. So what you do instead is you compare areas. So you compare the area of this education funding, say, with the area of this health funding, and you might conclude, even just with the perspective, that they're kind of the same. Whereas of course the education spending at 32 million is about half of the health spending in the 58 million. So this actually gives you almost nothing that a table wouldn't. So and again, this is what 6 points of information and a huge amount of space used. So this is terrible. Yep, next one. Pictorial graph. I treated Mark for his maths a while back, and I found this as one of the practice questions. We found this as one of the practice. Do you remember one?
Yeah, I remember.
So this is the hypothetical revenues and expenses for Telecom Australia in 1989 to 1990, and apparently this is a skill that people have to learn, presumably because of the shoddy state of graph making industry. You know, so what they've done is it's a telecom, so they made a nice little cute telephone, which is very, very cute. And so they've given you the total here, and they've split it up in a way that they haven't really described into the different categories of revenue, into the different categories of expenses. And you just get nothing. I mean, how are you supposed to compare this level, which is apparently $2 billion, to this level, which is also about $2 billion? I mean, what do you actually gain from this demonstration? Similar things happening here. I mean, it's just truly terrible. So the kind of fundamental, I'll go through the fundamental sins again, but the fundamental sin of this is it uses way too much space in a really, really confusing way. You could put this in a table, you could put this in a bar chart. There are 3 kinds of graphs that you need in Excel. Bar chart. No, that's not. Bar graph. So that's the ones that go across like that. So that's the one that kind of I made for the for when I was redoing the pie chart.
Horizontal lines.
So line chart. That's where you have time series. That's the one I remade for the university age structure. And a scatter plot, which I haven't mentioned, but you can ask me about in the Q&A if you'd like. Now the next one is just. I don't even know. I don't even know what to call that. So they split up China, Japan, Korea, and Vietnam. I believe this is a medical study. I only read it very briefly. And it's some kind of proportion of some kind of frequency with respect to some other variable. And presumably you're supposed to be able to read the distances up here for all 4 of these different things. And of course, it's impossible to do that because they're all hiding each other. And here. What are you even supposed to get from that? Like, okay, I'm going to measure China, so I go to this, maybe this 8 here, and I go up to the kind of white thing, and, do I go across? Do I go across and down because it's in 3 dimensions? Do I go across and up because it's in 3 dimensions? Nobody really knows. Please never use a graph like this. I don't think you can even do this in Excel. I don't know how he did this.
By hand.
And a pencil. These guys like, they will not comprehend the contents of this graph.
It's like he went out of his way. I'm going to say it's a he. It's probably a he. He went out of his way to make sure nobody understood what he was talking about. Next slide.
Also using different sample sizes.
Sorry?
The caption said he had
I didn't even look at the survey. The graph is enough to tell you what research of this is. So, according to Tufte, general characteristics of good graphs, and you can just negate these for bad graphs. Inevitably comparative. Graphs help you compare different numbers visually, and that's a whole lot easier if you have